Hi, I'm Alex doing Alex Things, and this is a video I made about a project I built because I wanted to learn about 555 timers. I also found that my baby daughter seems to really like Blinky Lights, so I decided to build her a box that she could stare at. My goals for this project were to use incandescent light bulbs, to have alternating blinking lights that are adjustable with a 50% duty cycle so that each lamp is on about the same amount of time, to have an adjustable brightness, and to not use a microcontroller. I'm used to using microcontrollers, so this was quite a different project for me. I've also never gone from using a breadboard to a perf board, so I learned a lot about that too. Anyway, let me show you a quick demonstration. So to turn it on, you just flip on the power button. This knob here controls the blink rate, and this knob here controls the brightness. So this is as slow as it'll blink. And this is as fast as it'll go. Then you can adjust the brightness. Let me turn this light off. So that's about as dim as it'll go. Like that. Slow it down. Then this is about as bright as they'll go. So all in all, very simple, but quite a bit went into doing that. Now that you've seen it work, I'll just kind of quickly go over the outside of it. So I've got an indicator LED, on-off switch, blink rate control, brightness control, two incandescent bulbs. They're just 2.8 volt flashlight bulbs with little plastic holders. Then on the back, 9-volt power in from a wall wart, a fuse. It's got vents there because I'm using LM317, so they put out quite a bit of heat. And then I had to drill a bunch of ventilation holes. This is more for the LM317s, and this is just to kind of keep everything else cool. Now that you've seen the outside, let's see inside the enclosure. So power comes in here through the 9-volt inlet jack, straight to a fuse, then over here to the power switch, which then goes to the regulators. This one controls the incandescent light bulbs. You see I kind of had to put a bigger heatsink on it just because of the current and the voltage drop going from 9 volts down to about 2.8 volts. Then this regulator here controls the VCC, the power that's going to be driving the circuitry in here. This timer here controls the blink rate, so the lights flashing on and off. This timer here controls the brightness using PWM. And this is just a little 5-volt relay that controls which light is getting the power from this LM317. And then I have 3 transistors here. I'll show you the schematics in a minute. One thing I did encounter with this was, like I said, I'd never done perf board stuff before. And one of the difficulties I had was initially when I wired everything, I daisy chained all of the connections. So I had like one power wire going to this 555, then to this capacitor, then to this timer. And that caused a lot of problems. The same with the grounding. I daisy chained all the grounds. So I ended up having to separate a lot of the grounds and some of the power because I had interference issues. Yeah, so it's not the prettiest perf board build ever, but for my first one, I think it came out all right. You can see this is where, I think it's called star grounding. I had to do that, split up a lot of the grounds. So anyway, that's the inside. Now that you've seen the project itself, I figured it'd be a good time to go through the circuit schematic just quickly. I won't get into too much detail, and I'll try to avoid going down rabbit holes while I'm just trying to give an overview. So power, I made this schematic too as I went, so it's not laid out in the most logical fashion, but power comes in down here through a power switch and a fuse. When the relay's on, it's pulling about 410 milliamps, and the relay's off, it's pulling about 320 milliamps, and the bulbs themselves each pull about 270 milliamps. That power goes to these 2 voltage regulators, The first one supplies voltage to everything except for the light bulbs, and the second one supplies voltage just to the light bulbs. Using this 1K trim pot down here, I set these resistors so that you could adjust it from 3 volts to about 7 volts, and I have it set to 5.5 volts. And that also powers the indicator LED on the front panel. The second LM317 is set so it's adjustable from 2 volts to 3 volts, and I have that set to 2.8 volts. Both of the 555 timers that control the project are set to operate in astable mode. The first 555 timer, which I called it the blink rate timer because it just controls how the lights blink, it uses this here, Q1, D1, D2, and these resistors to achieve roughly a 50% duty cycle, but have an adjustable frequency. And this is a really cool circuit, and I'll talk more about that in a minute. So the R8, the 100,000 ohm potentiometer, and the timing capacitor C2 are what allow you to adjust the frequency. And the output from this timer out of pin 3 goes to transistor Q2. And that just controls the power on or off to the relay coil, which if the power is on, one of the lamps is lit, and if the power is off, the other lamp's lit. That's how it works. So if you didn't have any power to the relay, just one of the lamps would be lit up. The second timer, the dimmer control timer, because it controls how bright or dim these lamps are, it uses these diodes and resistors to get your duty cycle adjustable. And without these diodes, you can't adjust this below 50%, but once you add these diodes, you can adjust it below 50%. So this 50,000 ohm pot R15, along with the timing capacitor C6, allows you to adjust the duty cycle. And the output from this goes from pin 3 to Q3, that transistor. And it operates at about 21 to 28 kilohertz using this 1 nanofarad capacitor. So it's just turning on and off these light bulbs really, really fast, depending on what duty cycle you set. And that's how you get the visual dimming effect. And that's basically how the whole project works. So to talk more about the timer 1 real quick, you can look up on YouTube. There's a lot of really good tutorials. My favorite was Circuit Breads. And I made this kind of flip chart for myself to understand the different states of the 555 timer and how it works internally. But to understand the first timer here, just know that pin 7, where's pin 7? Here's pin 7, is connected through a discharge transistor internally to ground. When the timer is outputting high, this transistor is off. When it's outputting low, it's on. So using Q1, R1, D1, and D2, when pin 7 is not connected to ground, diodes 1 and diodes 2 are not forward biased and they're off. And what that does is, since this node is not connected to ground and they're not conducting, R1 biases Q1 on because it forward biases the base to emitter junction. And that allows collector to emitter current to flow through R6 through this resistor network here, the potentiometer and everything, and charge up C2. Once C2 reaches the voltage that pins 2 and 6 internally into the 555, it's going to switch state. That's going to turn on that discharge transistor internally and connect pin 7 to ground. That's going to pull this node down, and that's going to forward bias D1 and D2. And what that does is that shuts off Q1, because now the base to emitter junction, if D1's on, you lose that forward bias, and so Q1's off. And so it's going to discharge to this resistor network through D2 into ground. And the reason that's useful in this case is because your charge and discharge paths, well, I'm not going to say paths, but the charge and discharge resistance is roughly the same. There's a little variations because of the internal resistor here, because of the diodes and whatnot, but is roughly the same. So you get about 50% duty cycle, but you are changing the resistance of both those cycles, charge and discharge. So you are changing the time it takes C2 to charge and discharge, and that means you're changing the frequency. But because both the charge and discharge paths have the same resistance, or roughly the same, you maintain just about a 50% duty cycle. Now you might be wondering about these resistors that are attached to the potentiometer. I did this just kind of by trial and error. I just started picking resistor values and adding them to the different legs. I took a whole bunch of notes, just trying to figure out, what combination worked the best. I found if you didn't have any, the blink rate was kind of unstable, like it would jump steps as you adjusted the potentiometer, and it would blink way too fast or way too slow. So I just started cobbling together different combinations until I got a combination that I liked. And I also added this 20K trim pot here just so I could set the fastest or the slowest blink rate I wanted after I built the whole thing, because it acts differently on the perf board than it does on the breadboard. So yeah, in case you're wondering where these resistor values came from, I didn't do any fancy math, I just did trial and error. And then over here, you're probably noticing that both my 555s are not connected straight to VCC here. They're connected to it through a RC low-pass filter. And if you remember, the formula for the cutoff for low-pass filter is FC is equal to 1 over 2 pi RC. So this one here is set to about 31 hertz. So anything above 31 hertz, it starts to attenuate. I did that because I was running into some weird interference issues. When I added these bulk capacitors over here, C16 in particular, that really smoothed how the bulbs looked as I did the dimming the PWM. But it had an unintended consequence of having this weird coupling between the PWM potentiometer and the blink rate. So like when I would adjust the PWM, I forget exactly what settings I had, but I would be adjusting the PWM and my blink rate would suddenly start acting up and seem a little odd. And so what I ended up doing was I put a low pass filter on here so that the PWM frequency wouldn't get through to it, or wouldn't get through to the timer as strongly. 555s are fairly sensitive, from what I've discovered, to any kind of wobble in the ground or the power rail, because internally it's just comparing voltages before it switches state. So if you have wobble, it can like have false triggers and act up. So that helped significantly when I put this low pass filter on here. The other thing that really helped was separating the grounds. If you remember when I talked about the perf board, I had that big glob of solder because I had to take a lot of the daisy chained grounds off and just do dedicated grounds from one point where the power supply came in. I also did that with a lot of the power. Instead of daisy chaining from like here to here to here to here, I just separated them all and ran them back to the LM317 itself, and that seemed to also help significantly. So for the second timer, the dimmer control, it uses D4, D5 to kind of steer the charge and discharge paths. Without those diodes, you can't get below 50% because in astable mode, like this is the textbook way this works, is the charge path is through R1 and R2, charges up the capacitor, and the discharge path is only through R2. So the only way you can get even to 50% duty cycle is to make R1 extremely small compared to R2, but you can't get below 50%. So the way around that is you add a couple diodes. So when the timer output is high and the timing capacitor C6 is charging, using R11 to charge this through D5, you're forward biasing this diode. It charges through this path. Then once it gets up to the voltage it needs to switch state, it's going to discharge, because pin 7, as we talked about, that's going to internally connect to ground. It's going to forward bias D4. D5 is going to no longer be forward biased, so it'll be off. So the only way C6 can discharge is through this path here and to ground. Now what that means is your relative amounts of charge and discharge based on where you set the potentiometer are going to be different. So you can control your duty cycle. Now your frequency is going to vary a little bit because you are changing the resistance. One interesting thing to note was initially I had, I think it was a 0.1 microfarad capacitor. Let me check my notes. Yeah, so initially I had a 0.1 microfarad capacitor for C6, and I had a frequency of around 200 hertz. Now that worked fine on the breadboard here, and I also learned a lot about this particular case. There's a lot of stray capacitance, so a lot of those interference issues I mentioned where I had to use a low-pass filter, they did not appear on this because, as I later learned, there's stray capacitance, and that can sometimes hide issues like that. And it also hid the 200 hertz buzzing that I got. So I had to drop this capacitor significantly, so now it's 1 nanofarad, and that raised my PWM frequency from around 200 hertz to around 21 to 28 kilohertz. And that took care of all the audible buzzing, and I think just some components were vibrating, and since it's in the audible frequency range, you can hear it. Drove me crazy. But what that necessitated was I had to change out D4 and D5. They were the same rectifier diodes, the 1N4004s, but I had to change them out to something that was quite a bit faster. So I changed them out to 1N4148s. Another thing to note was these resistors here, just like how I kind of experimentally found these values that I liked, I did the same thing here. So now keep in mind, this was when I had the capacitor at 0.1 microfarad. So this is for a different frequency range, but the duty cycles relatively are about the same. So if I had just 1K resistors on the end of each of the 50K pot leads, that gave me a duty cycle adjustable from 95% down to about 7%. And the 50K pot alone gave me 100% to 2.5% duty cycle. Then if I changed R14, the bottom resistor, from 1K to 20K, that brought it up to 31% for the lowest duty cycle. And you can see if I change the top resistor R12 here, that brought my maximum PWM down to 71%. And then if I change just the wiper resistor, that gave me 76 to 24%. Now the reason I did that was so that when I had the PWM knob turned all the way down, I wanted the filaments to just barely be lit. And of course, the highest PWM, I wanted them to be full brightness. Okay, so the last thing I wanted to talk about was Q1, Q2, Q3, and R10 and the power calculations. So I made this sheet here. It's just a table of a bunch of measurements I made. Now, I took all these measurements on the breadboard, and they were taken when I was at around 200-ish hertz. So that was before I dropped down the timing capacitor on the timer 2. But they're still roughly the same. So for Q1, I didn't even bother doing any power calculations because IC's only 0.19 milliamps and IB's 1 microamp. So I didn't even bother worrying about any power for Q1. For Q2, its collector current is essentially the current through the relay coil. So it's 85 milliamps. So it's dissipating, because it's in saturation, it's 0.15 or 0.2 volts. And you can see both the base to emitter and the base to collector junctions, they're both forward biased. So the transistor is definitely in saturation. And because it's in saturation, it's only dissipating 17 milliwatts. And the power dissipation for the 2N2222A, the maximum is 500 milliwatts, so you're well within that range. And IC max for that transistor is 600 milliamps, so you're also well within that range. Now for Q3, I did measure the power dissipation at 100%. PWM setting is equal to 270 milliamps. I saw 270 and 260, so I just used 270, times the VCE of 0.29 volts. And that got me about 78 milliwatts, which is well within range for that transistor, and the current's also well within range. Now, when I say 100% PWM setting, what I mean is the knob itself was turned up to 100%. It doesn't necessarily correspond to 100% duty cycle. The actual duty cycle is probably closer to like 95%. And when it's at 50% and 25%, this doesn't necessarily mean 50% duty cycle, 25% duty cycle. It just means I put the knob at roughly 50%, 25%. Now these readings were all taken with my multimeter, and as I later learned, they're a little bit misleading. So I thought that the transistor was actually dropping out of saturation, because you see down here, 50%, it was at 1.6 volts, and then it creeped up to 2.29 volts, and then up to 2.65 volts, which if you did that calculation for 50% knob setting and 25% knob setting, your power dissipation jumps up from like 80 milliwatts to 250 milliwatts. I later found out this I don't think is the case. Number one, because I actually felt the transistor and it didn't feel like it was getting that warm. And two, because I put the Q3 on my oscilloscope, and so I just measured the voltage collector to emitter. So just collector to emitter. And if it's in saturation, it should still be fairly low. So at the minimum R15 knob setting, I got a frequency of 20 kilohertz, and the pulses were about 0.5 volts. And at the maximum knob setting, I got 28 kilohertz, and the pulses were about 0.3 volts. So this kind of tells me that even at the lowest PWM setting, I'm still in saturation, even if it's a little bit weaker. And at full PWM setting, I am definitely deeply into saturation. So these readings here, while they initially looked concerning to me, I kind of learned a lesson in, understanding that these are average values, and they kind of threw me for a little bit of a loop, because I thought I would have way more power dissipation than I actually ended up with. So that was something interesting I discovered. Then for R10, the current I measured through it was about 30 milliamps and about 3 volts. It was quite a bit less than that, but I just did that to be conservative. So I got a power dissipation of 90 milliwatts, which is well within range for a quarter watt resistor. But I just upgraded to a half a watt simply because I could. It was easy and it felt a little bit warm. And since this box does get kind of warm inside, I figured it would be better to just upgrade it. And last, if you're wondering why I used a relay instead of a MOSFET or something like that, well, I just think the clicking noise is something my daughter might like. Kind of adds a little bit of a audible part to it. I hope you found this video informative. If you liked it, please give it a thumbs up or subscribe. As always, may the Lord bless you and keep you. May the Lord make his face to shine upon you and be gracious to you. May the Lord lift up his countenance upon you and grant you peace. By the power of the Prince of Peace, Yeshua. Amen. See you guys. Shalom.